All right, we're going to take a look at the thermochemistry lab, the Hess's Law lab. And the first thing we're going to take a look at is the 4 reactions you go through. The first one involves just water solutions. So you have 2 volumes of water, say 30 mils, 50 mils. And one of them is room temperature, T cool. The other one is something you heat it up to, 70, 80, 90 degrees Celsius. When you mix them together, you would expect a very average temperature to come out of it, a T average. So you have something we're going to call T average, and it's expected between these two. I just divide the average of the 2 by 2. But when I mix them together, and I kind of stir in the coffee cup here, this is our calorimeter we're going to use. When I put it into the calorimeter and stir it and record temperatures about every 20 seconds or so, and eventually put that into a graph, if I extrapolate that back and get the y-intercept off my calculator, it's going to give me a value probably a little bit lower than what I expected, the T average. And we're going to call that value a T mix. And it's lower because some of that energy that you would expect to find is actually lost to a variety of places. The thermometer, some just goes out the top, and some of it is absorbed by the calorimeter. We're going to assign all the energy directly to the calorimeter. So with this part here, we're going to talk about these 3 values and just look at the calorimeter, which is probably the most confusing part. The first part is to look at the discrepancy between the T average and the T mix, what we expected. If we take the volumes, multiply it times the constant, which is 4.184, and then multiply it times that change in temperature, the discrepancy, T average and T mix, that'll give us an energy value that's unaccounted for the calorimeter. If we take that value that we are accounting for and divide it by the temperature range that the calorimeter moved, or the temperature change it was exposed to, and this is the part we have to be careful with. We divide it by 2 different numbers, the T cool, because that's the temperature it's starting at, and the T mix, the temperature it actually went up to, that'll give us the energy absorbed by the calorimeter over a specific temperature, 1 degree Celsius. And we're going to use that value in this equation here for the other 3 reactions. So let me go back really quick to the lab. You're going to have 3 other reactions you're going to run. Equations 1 or reactions 1, reactions 2, reactions 3, equations 1, 2, and 3. It involves some HCl and some NaOH for the first one, and you can look at the other ones on your sheet. The process is exactly the same. 2 volumes, probably 30 mils of 2 molar solutions. You'll put them into the calorimeter. Everything's room temperature at this point, so T cool. You don't have to keep checking it. As long as you know what room temperature is, it's the same everywhere. And then the temperature is going to go up. You measure the temperature change every 20 seconds or so and get a graph. With the graph, again, extrapolate back to the y-intercept, and that'll give you the T mix for each one of your reactions as you're going through it. Having the T mix, with that part there, you can go through and take a look at this reaction. So let's talk about the negative sign. The negative sign is just a fix. It's not really mathematical. It's a fix demonstrating this is the energy released by the reaction. So if the energy is released by the reaction, it's the same amount of energy, conservation of energy, that is absorbed by 2 things, the water and a cup. So here's the water portion, and here's the cup portion. Remember, we're assigning all that energy loss that we expected to the cup. So here's the equation. We have the mass of the water, and I give you a conversion for the density of the solutions. So if you have 30 mils and 30 mils, that's 60 mils, times the density of the solution. You'll put that in for the mass, 60 point something, times the heat capacity of the water, 4.184 joules per grams per degree Celsius, and then times the difference between room temperature, T cool, and T mix. This is going to be the value you're going to use for this reaction here. Over here, this is the exact same value. So these 2 are both exactly the same. So that's pretty well taken care of. This is a constant that you would have developed earlier, the first part of the lab for the calorimeter. So this value goes for all three reactions. This is the only thing that's changing for each one. And T-cool, you know what that value is for all three of them. That doesn't change. It's just the T mix that you have to get graphically for all three reactions. So once you have that part done, you have a energy released by the reaction for all three, or in this case, this is what's absorbed by the water in the cup, which is equal and opposite sign for the reactions. You're going to take those values and using Hess's law, you're going to compare equations 1 and 2, rearrange them to create equation 3, and if things work well, it should be close. Rearranging equations 1 and 2 to make equation 3, the energy value. If it's different, then that is your percent difference. So again, to explain this again, you actually ran experiment 3, and you got a value for it. So you actually have it. You can use equations 1 and 2 to theoretically get reaction 3. So it's a comparison of those two to generate a percent error. There you have it.